Hi, this is Professor Fernandez. This is the first video in Lesson 6. We are talking in here about the limit laws and specifically how to evaluate limits using the limit laws. I'm going to go through 3 examples here from Calculus Simplified to show you how to apply those in practice. So let's go through the first one here, example 2.17. I'll zoom in a little bit. So it says evaluate the limit as x approaches 1 of this quadratic expression. So as a very quick review, the limit laws that are on page 22 of the book, Calculus Simplified, this is theorem 2.6, they basically tell you that the limit of a sum of functions is the sum of their limits, the limit of a difference is the difference of the limits. There are kind of rules like this, and also the limit of a multiple of a function is the multiple of the limit of the function. And again, you can go to theorem 2.6 to see the exact statement. So if everything goes according to plan, so to speak, then everything I just said, the examples I gave of the limit laws hold. So really, when you apply the limit laws in practice, what you try to do is, the shortcut is use them as you would normally until if it so happens that you get to a point where the limit you're evaluating does not exist. Then that's kind of a clue that the limit law does not apply. Because part of the hypotheses for the limit laws theorem is that each of the individual limits you break up this big limit to actually exist. So I'll show you that here. So first thing we can do is we can say, oh, there are 3 component functions in this quadratic expression. So I'm going to split up the limit in terms of those component functions. So there we go, minus the limit x goes to 1 of 1. And this is what I was saying earlier. If any of these 3 limits did not exist, then I would not be able to do this split as I just did. That's a precondition of the limit laws theorem, that whatever limits you split your original limit into actually exist, and therefore you can do the splitting. Then I'll do one more split. This 2 is a multiple, so I can bring that outside. This is another limit law. And then one of the things that limit laws does, which you can see is happening here, is that it converts a fairly big limit, this one that we started with, into a sum of or difference of multiples of smaller limits, limits of functions that are a little easier to deal with. And then the last thing we can do here is this x squared, another limit law property. The limit of x squared is the limit of x squared, right? Makes sense. A lot of these limit laws, when you say them in English, they make sense in that way. So at this point, I have broken down the original limit into the most simple form that I can think of. And the beauty of the limit laws is that I am now left evaluating 3 very simple limits, right? And we can just, again, talk about this, say this out in English, and we'll see what the answers are. So the limit as x goes to 1 of the function x is, well, x is going to 1, so that's 1. And then over here, same thing. The limit as x goes to 1 of x is going to 1, so also 1. And then the constant function, y equals 1 over here, doesn't matter if we approach x equals 1 or x equals 7 or 19, its y value is always 1, so that limit is 1. Great, so then we do the arithmetic here. These ones cancel. The 1 over here squares to 1, multiplies by 2, so I get 2 as my answer for this one. All right, so I'm just going to illustrate how we keep using these limit laws and talk about a few of the other limit laws. Here's a new one in this example. This limit is the limit of the square root of x plus 1. So again, we're going to start off like we did before. We're going to assume that I can actually slide this limit inside under the square root. That is one of the limit laws, again, provided the actual limit I get from this calculation does not lead me into trouble. For example, if I got something like square root of -5, then I would know that there's something wrong, and that would be a tip-off that I can't apply this limit law that I just did. So let's continue the calculation, make sure nothing like that happens. So I'm under the square root here, so now I can effectively distribute this limit. It's another way to think about what limit laws do in that sense. Great, so I am left therefore calculating 2 one-sided limits. So I have this one and that one. This one is, again, like what we said before. as x approaches 0 from the right, x approaches 0 from the right, so 0. And then same deal here. The function y equals 1 is constant, so x approaches whatever number, its y value remains that constant, which is 1. So I get the square root of 1, and that's 1. So that's my answer for the limit. Again, in these examples, there's nothing that's going wrong after I apply the limit law, so I'm able to carry out the calculation without any trouble. Okay, so now 2.19, so evaluate this limit. This one involves a fraction, so again, it's another chance to talk about that limit law. So that limit law says that the limit of a quotient is the quotient of the limits. Again, provided that each of these limits exists, and also that the limit of the denominator does not give us 0. Okay, so we're going to have to check that here. All right, in the numerator, then I can distribute the limits, and I can also use the fact that we used before, that the limit of x squared is the limit of x squared. And then I can pull out the 9, be left with the limit of 1 up here, and then divide it by limit as x goes to 3 of x minus 2 times limit as x goes to 3 of 1. Great, so you can now see again the 4 component limits that I'm left evaluating. And I know that this limit is 3 because I'm looking at the function y equals x as x approaches 3, so that's 3. I know that this limit again is 1. We've done this a few times now. So the numerator is 3 squared minus 9 times 1. And then denominator down here, y equals x, x approaches 3, this limit is 3. Y equals 1, x approaches whatever, it's still 1. So numerator, denominator is 3 minus 2 times 1. So what do I get? So in the numerator, I get 9 minus 9. Denominator, I get 3 minus 2. So that's 0 over 1, which is 0. So that's my answer for the limit. Again, nothing went wrong. I did not get a 0 in the denominator, for example. There were no other limits. None of these 4 limits ended up not existing. Those would have been tip-offs that I can't use these limit laws. So that really is it for the limit laws. One thing I'll say, if I remove all of the clutter that's on this page, which, I guess it's not really clutter, it's the work that we just did to get all these answers. If I remove that, where we are in the course right now and where you might be watching this video, this is a video about the limit laws, right? So your instructor, including me, if we ask you about the limit laws, we might want you to justify or cite, this is limit law number 4, number 7 or something. Truth be told, in the real world, right, you would not normally evaluate, for example, this limit through all the stuff that I just erased here, right? This long list of steps. You would just say some version of, well, this is a polynomial. Polynomials are continuous. So I can just insert x equals 1 in here, and I will get the output, which is the answer to the limit. Or you could just reason this out based on what you know about limits. If x is approaching 1, x squared is approaching 1 squared, x is approaching 1, right? And then you just do the math like we did before. This gives you 2. So all of this is to say that the question, use the limit laws to evaluate the limit, is really a question more about getting you comfortable with the limit laws and not really a question about evaluate the limit using the fastest way possible. Generally, that's not the limit laws. Great, so that's all I wanted to say, and I'll see you in the next video.